So we've discussed how you've got an electron in the system. Let's say that this is hydrogen and there's only one electron. It can jump up to a higher energy level if it absorbs the right amount of energy. And then once it's there, it will sit there for some period of time. And then eventually it will fall back down. And when it does, it has to release energy from the atom to do that. And that's what you'll see as color in your eye if the energy falls in the right range for color. If the energy falls in the UV range or the IR range, you won't be able to see it unless you've got like IR glasses or something, but you won't be able to see it with your just your eye. But if it does fall into the visible range, then you'll be able to see the color. So what was it that Bohr did that made everyone pay attention to what he was thinking? So he came up with an equation to calculate how much energy the electrons would have to have at the different energy levels for hydrogen. And so for example, when N is 1, he calculated that the RH is a constant up here. And by the way, if you Google this, RH actually has other values. One of them is a meters value. So make sure you're using the correct RH with this equation. You know chemistry. You got to make sure you pick the right stuff. So this is 2.18 times 10 to the minus 18th joules. And if we want to know the first energy level, it's 1 over, and the equation might seem weird, but N is just the energy level. So it's just the first energy level squared. So 1 over 1 squared is just 1, which gives us negative 2.18 times 10 to the minus 18th joules. So this gives us this electron, and it's the one that's in this path right here. It gives us that one's energy. So that's really, really simple. And he did this and he calculated the energy for the different levels. So you can now work this problem and calculate different energy values. If we wanted to go ahead and do it for the second electron, we would take the exact same equation, except that we would put a 2 in instead of a 1. So again, this is for the first energy level, and this would be like for the second. So same equation, but this would now be a 2 because it's the second energy level. And when we plug it into the calculator, we would get negative 2.118 e to the negative 18th times 1. I don't know why I have a 5 in there. 1 divide. And you could say 2 squared, or you could just say 4, because that's what 2 squared is 4. And we plug it in, and we get that the second energy is 5.45 times 10 to the minus 19th joules. That's the energy of the second level. So I'm going to color code that. So it's like saying right here, this one's energy on this level. So this is great, but what he did that made everyone pay attention is that he matched his numbers up with the line spectrum, the ones that we've talked about, those glowy colors that are made up of different wavelengths. He was able to match wavelengths with the energy differences. So he didn't just use this equation, he actually calculated the difference in this number, which isn't hard, right? And then in this number, oh, I left off my negative here. Don't leave off the negative. So he calculated the difference in those numbers. Now, there's an equation that lets you do this, so you don't have to calculate them separately. It's a little bit less work to use the equation. But in both cases, you're going to get the same number. So if you want to put this in your calculator and make sure you get the same number the equation I'm about to show you gives, that's fine. So if you look right here, at the top of this section right here, I've got the equation. You'll notice it's very similar. I'm going to try to get them both to show up. So this is RH and then times just the n squared. So now instead of just any n squared, it's specifically the first one, the initial one you were at, and then the final one that you were at. So we went from the second energy level, because that's the second one, to the first energy level. So if we want to use this equation, it's just saying that we're going to go from the second energy level, and that's squared, to the first energy level squared. So I'm going to go ahead and fill this in over here. 2.18 times 10 to the minus 18th joules. Second energy level, that's the 2 squared And then, of course, basically I have 1 over 1, but that's 1 over 1 squared, which is still just 1. And when I put that in my calculator, I'm going to get, I'm going to go ahead and carry down my number, that minus 1. I can do 1 over 1 squared, but it's just going to be 1. And that gives me that my energy difference is, whoops, 1.635 times 10 to the minus 18th joules. Now, when you look at that number, it doesn't really mean anything, so I'm going to put it in the context of what they knew. So he did this for, and there were people who double-checked him on this too. He did this for not just this spacing, but he did it for this spacing and this spacing. And then, like, you can calculate it for that distance. You don't have to do, you know, you can find any of the different distances and you can calculate them, the energy differences. So if you take this number and you plug it into the equation we already know for energy, do you remember using this one? E is hc over lambda. I've already plugged it in because you know how to do it and I'm just trying to save time here. So this is the energy we calculated. I should highlight it. So right over here, this is the energy that we calculated. And it's going on the bottom. So that's the number we just calculated. And then those are those two constants you've already used. You should be a pro at now. When you plug it in, you're going to get this number here, but it comes out in a meter. And all of these are nanometers if you look at them. So I had to convert it into nanometers to make this make sense, to make my point. But for the second and the first energy level, there actually is a wavelength that matches beautifully with this value. And if you do that for all the different energy levels, you will find a different wavelength that matches with the values. It's very, very cool. And everyone was so impressed with this, they began using this model. It's also a nice simplistic model that you can draw really, really easily. It's often called the planetary model because, again, the electrons are traveling on a orbit, like a planetary orbit around the nucleus.